Hey guys, so today we're doing a quick and easy lesson continuing on with our gases unit. We're going to be going over some of the different factors that affect gases like volume, temperature, and pressure, and then there'll be one little calculation at the end that you guys will have to do. So this is our lesson on temperature, pressure, and volume of gases. You do need to know kind of what we mean by those different terms, how we measure those different terms, like what the units are and stuff like that. Then we'll be doing the law of combined volumes and Avogadro's law, and using that to determine the volume of a gas. So temperature is important because it affects the kinetic energy of molecules, which is essentially how much those molecules are moving. As temperature increases, so as it gets warmer, those molecules are going to move faster and therefore have more kinetic energy. If you decrease the temperature and make it cooler, those molecules are going to start moving more slowly and therefore lose kinetic energy. In real gases, eventually they will lose enough of their kinetic energy and slow down enough that they will condense or become a liquid. Though we talked about in the KMT how ideal gases don't ever actually condense because they don't have forces of attraction between them. Since real gases do actually have weak forces of attraction between them, once you slow them down enough, by cooling them down enough, they will actually condense. In like everyday uses, temperature is usually measured in Celsius or Fahrenheit, though in a lot of calculations and in science, a lot of the time we use Kelvin instead. All of the gas calculations that you are doing this unit should be done in Kelvin. There are some where it actually won't work if it's not in Kelvin. Other ones, it's not as important, but it's always just good practice to convert your temperature, which will often be given to you in degrees Celsius, into Kelvin instead. The way we do that is just take the temperature in degrees Celsius and add 273.15, and we get our temperature in Kelvin. Just so you know, Kelvin doesn't have like a little degree, it's just a capital K. The next factor is pressure, which refers to the amount of force a gas has pushing down on a given amount of its surface. It's calculated by taking the force and dividing it by the area, though you won't actually have to do that calculation this year. If we're talking about atmospheric pressure, that is the amount that gases in Earth's atmosphere press down on Earth's surface. We use something called the barometer to measure atmospheric pressure, which is this circular device here. This is a barometer. And then manometers are used to measure pressure in closed systems, which is this kind of strange looking device on the right-hand side here. Pressure can be measured in a bunch of different units. Atmospheres, or ATM, is usually used to measure atmospheric pressure. Millimeters of mercury is used sometimes. That's the mmHg. Torr is less common, so is bar and millibar. Pounds per square inch, you've probably heard of before, PSI. I feel like that's used to measure things like tire pressure and stuff like that, though sometimes millimeters of mercury is used as well. Pascals and kilopascals can also be used. A lot of the time in our gas calculations, we will use kilopascals, though atmospheres can also be used in some of them. So those are the two big ones that we'll be using, is atmospheres and kilopascals. When we're talking about standard temperature and pressure, these are amounts that you have to be familiar with. So standard temperature and pressure, STP, is 1 atmosphere, which is the same as 101.325 kilopascals. It's easier to remember just 1 atmosphere of pressure and 0 degrees Celsius. So 1 atmosphere of pressure, 0 degrees Celsius is our STP. Of course, in any calculations, you would have to convert that 0 degrees Celsius into Kelvin by adding 273.15. Standard ambient temperature and pressure is SATP, is also at 1 atmosphere, but it uses 25 degrees Celsius instead of 0 degrees Celsius, since 25 degrees Celsius is closer to room temperature and most experiments occur at room temperature and not 0 degrees. So So those are things that you need to memorize. STP is 1 atmosphere and 0 degrees Celsius. SATP is 1 atmosphere and 25 degrees Celsius. And then the third factor is volume, which is just how much space the gas is taking up. As molecules spread out, which usually happens if they get warmer or if you have less pressure on them, they're going to become less dense and take up more space, so the volume will increase. If you decrease the volume, usually by putting pressure on the gas or by slowing down the molecules by cooling them, those gas molecules will become closer together and therefore denser. So yeah, if you increase pressure, the volume will decrease because you're going to press those molecules closer together. If you decrease the pressure, you'll allow those molecules to spread out more. The law of combining volumes is just a law that says if you combine 2 or more gases in a chemical reaction and you keep the temperature and pressure the same, the volume of the gas reactants and the volume of the gas products will occur in a simple ratio of whole numbers. It can't tell you what that ratio is going to be, just that it's going to be whole numbers. In order to actually figure out what that ratio is going to be, we use Avogadro's law. Avogadro's law describes the relationship between the volume of a gas and the number of moles of that gas. So you will have to think back to the chemistry unit of science last year where we talked about moles. It can be used to determine the ratio of gas volumes in a reaction, which you can then use to predict the volume of a product that is going to be produced. In this case, you would need to know the chemical equation for the reaction and the volume of the reactants. You then balance the chemical equation to determine the ratio that you're using and go from there. As the volume of gas changes, the amount of moles will change proportionally, since if you have more of a substance, it's going to take up more space. By saying it changes proportionally, what that means is if the volume goes up, the amount of moles goes up. If the volume goes down, the amount of moles goes down. So they change in the same direction as one another. Again, that only works if you're keeping the temperature and the pressure the same. Because as soon as you start changing temperature and pressure, that also affects volume. The mole ratio is the balanced chemical equation. That is going to be proportionate to the volume ratio of the gases. And we can just see the mole ratio just by balancing the chemical equation and then looking at the coefficients, which are the big numbers in front of each molecule. So let's go through this example here. It says we're reacting 4 milliliters of ethane gas with oxygen to produce carbon dioxide and water vapor. Now, just so you know, if this was a question on the test, it would have to tell you what ethane is, because that's not a molecule that you need to know, but the rest of this you should be able to write. Find the volume of oxygen needed and the volume of carbon dioxide and water produced. So our first step is to write the chemical equation. Again, you would have to be given this formula for ethane, because that's not one that you would know. You would have to know that oxygen is O2 since it's diatomic. You would have to know that carbon dioxide is CO2 and water is H2O. Our next step is to then balance that chemical equation, identify the mole ratio, which is the coefficients, then identify the ratio of the volumes and set up a ratio to find the actual volumes. So let's switch over to my document camera and we can work through this problem. Okay, so I've got my equation written out here, and the first thing I need to do is balance this. So I'm going to look at my C's first, and I have 2 carbons on my reactant side. I only have 1 carbon on my product side. So I will add a coefficient here. That now applies to both the C and the O. So now I have 2 carbons on both sides. Then I'm going to look at my H's next. I've got 4 H's on this side. I've got 2 H's on the other side. So I will put a 2 in front here. And now I have 2 times 2 is 4 H's on this side to match the 4 H's on the other side.
The last thing I have to look at is my O's. I have 2 O's on the first side here, and then I have 2 times 2 is 4 O's in my carbon dioxide, plus 2 more O's in my water, for a total of 6 oxygen on my product side. In order to get 6 oxygen on my reactant side, I have to put a 3 in front of the oxygen. 3 times 2 is 6 oxygen. So now it's all balanced. The next step is identify the mole ratio, which is just the coefficients. So that is an imaginary 1 to 3 to 2 to 2. So that is also the ratio of our volumes. Then it says set up the ratio of our volumes to the actual volumes and go from there. So I am given the volume of ethane gas as being 4 milliliters. So to go from ethane gas to oxygen is a 1 to 3 mole ratio. I know that I have 4 milliliters of the methane. I want to know how many milliliters that will be of the oxygen. So I'm just going to cross multiply. X times 1 is X, and 4 times 3 is 12 milliliters. So I will have 12 milliliters of oxygen needed. And then I'll just do the same thing for my carbon dioxide and my water as well. So ethane to carbon dioxide is a 1 to 2 ratio. Again, it's 4 milliliters to an unknown amount of milliliters, and then we cross multiply. X times 1 is X, 4 times 2 is 8 milliliters of carbon dioxide. And then ethane to water is a 1 to 2 ratio as well. So it's also going to be 8 milliliters. Okay, so we just set up a proportion using the volume that we were given as well as our mole ratio, and then cross multiply and divide. Avogadro's law is really just a formula that summarizes that process. So you would do all the same thing, but this is just the formula that represents the cross multiplying and dividing that we're doing, where we have the volumes that we were given and the volumes that we were finding, as well as our mole ratio. So in this formula, the N1 and the N2 is just essentially our mole ratio, our coefficient. So it's essentially just what we were doing, but flipped upside down, which doesn't actually change anything. So using either Avogadro's formula or just this ratio that we set up, try to solve this question. So pause here, solve this question, and then come back for your answer. Okay, so the first step is to just write out our chemical equation. And so the first thing you have to know is that we have chlorine gas. Chlorine is diatomic. It's one of our Hofbrinkel molecules, so we need that little 2 there. It's reacting with ozone, which is O3, to produce chlorine dioxide. And so this is a molecular compound. That prefix of di in front of the dioxide tells us that there's 2 oxygen. And since the chlorine doesn't have a prefix in front of it, it's not like trichlorine or tetrachlorine. That means that there's no little number behind it. So this is what your formula should look like. And then in order to balance it, you might start by trying to put like a 2 here, but that's not going to work. So eventually, if you just keep going to bigger and bigger numbers, you'll get that you need to have a 6 there, a 3 here. Now my chlorines are equal. There's no way to get them equal without going to that big of a number here. And then for my oxygen, I have 6 times 2, which is 12 oxygen. which means I have to put a 4 in front of my ozone, since 4 times 3 is also 12 oxygen. So now this is balanced. I have 12 oxygen on either side. I have 6 chlorine on either side. Then I am going to use my Avogadro's law formula. So V1 over N1 equals V2 over N2. It told me my amount of chlorine gas. So we're going to start with figuring out my amount of ozone. So I'm going to go from my chlorine to my ozone. My volume of chlorine, again, using this formula here, my volume of chlorine was 35 milliliters. I don't know the volume of ozone. The mole number, so the mole ratio of chlorine is 3, and for ozone, it's 4. So that's what these little n's refer to, is just that mole ratio number in this case. And then I'm going to cross multiply. So 3 times x is 3x. 35 times 4 is 140. And then, of course, to isolate the x, we just divide by 3. And we get 46.67 milliliters of ozone is what is required. And then it wants to know how much chlorine dioxide is produced. So again, we're going to do the same thing. This time we're going from chlorine gas to chlorine dioxide. Once again, we have the 35 milliliters of chlorine gas. We don't know the volume of chlorine dioxide. Our N value for chlorine is 3. It is 6 for chlorine dioxide. And then we cross multiply. 3 times x is 3x. 35 times 6 is 210, and then divide by 3 to isolate the x. And we get 70 milliliters of chlorine dioxide. Make sure when you're doing this that you are carefully labeling what you found the volume of, so don't just circle your number. Make sure you're also telling me what molecule it was. If you don't, you won't get full marks for this. Okay, that's it. Again, you can do it either this way or the way that I went through the previous question, whichever one makes more sense to you. I actually prefer the previous method where the whole, where like our mole ratio is on top of the fraction and the volume is on the bottom. And then this one's just upside down from that. But again, it doesn't make any difference. Either way, you're just going to cross multiply and divide, and you will get the same answer regardless of how you solve it. Let me know if you have any other questions.